At around 9:30 on the morning of October 15, 1891, the great cast-iron flywheel driving every machine inside Mill Number 7 of the Amoskeag Manufacturing Company in Manchester, New Hampshire, ripped itself apart at full speed, hurling chunks of iron 200 feet through brick, timber, and steam pipe, and killing 3 people in the time it takes to draw a breath. That wheel weighed somewhere between 64 and 68 tons, stood roughly 30 feet across, and through a network of shafts and belts it was, moments before it failed, the single source of motion for carding machines, looms, and hundreds of other machines running across 4 connected mill buildings. It was not the first time this exact engine system had turned on the people who ran it. 3 years earlier, in 1888, it had already killed a man, an engineer named William Venable, and the mill had gone right on running it. The morning it finally came apart, the trouble was not showing up evenly across the complex, which made it harder for anyone on the floor to read in time. In the southern end of the mill, carding machines were losing speed for no reason the operators could point to, while at the very same time, in the northern end, the looms were speeding up, and at least one loom's own governor, the small mechanical safeguard built into the machine specifically to keep its speed under control, had already failed to hold it in check. If you enjoy these documentaries, then subscribe. Thank you. Now back to the gritty history. To understand why an iron wheel spinning inside a New Hampshire textile mill could become one of the most concentrated stores of destructive energy in the entire building, you have to understand the problem it was built to solve in the first place, because the flywheel was never an accessory. It was the fix for a defect built into the steam engine itself, and the story of how that fix grew, decade after decade, into something powerful enough to level a mill floor is the story of an entire century of industrial power. A piston steam engine does not produce power in a smooth, continuous push. Steam enters the cylinder, drives the piston down or across, and for that portion of the stroke, the engine is delivering real force to the crank. But between power strokes, and especially at the 2 points in the crank's rotation known as dead center, where the piston is at the very top or bottom of its travel and its thrust lines up directly with the crankshaft, the engine delivers essentially no rotational push at all. Left to itself, a single-cylinder engine at dead center has nothing turning it forward. It can stall right there, mid-rotation, with a full head of steam behind a piston that is, for that instant, mechanically useless. Picture the crank arm of an engine like this, sweeping through a full circle. For part of that circle, steam pressure behind the piston is shoving hard against the crank at an efficient angle, and power pours out. For another part of the same circle, the piston is still moving, but its push lines up almost uselessly with the shaft, contributing little. And at the 2 dead points, top and bottom, the push contributes nothing measurable at all. An engine running completely alone, with no reserve of motion carrying it through those dead points, delivers a rotation that surges, sags, and at the worst possible moment, under a sudden new load, can stop outright. Early millwrights and engineers who connected these engines directly to gearing, saws, looms, and line shafts learned quickly what that irregularity cost them. Power surged in and dropped away in a rhythm that matched the piston, not the needs of the machinery downstream. Gear teeth sheared off under the sudden peaks. Leather belts, already under constant tension, snapped at the jerks. In a spinning mill, uneven rotational speed meant uneven twist in the yarn, thread that varied in strength and quality along its own length. In a press shop, it meant stamping force that came in hard on one blow and weak on the next. Saw blades chattered instead of cutting clean. And under any sudden load, an engine with no reserve of motion to draw on could stall, the entire line of machinery lurching to a stop with it. The solution engineers arrived at was mechanically simple, even if its consequences were not. Mount a heavy wheel on the engine's output shaft, build most of its weight into a thick outer rim rather than a solid disc, and let that spinning mass do the job the piston alone could not. During the power stroke, when the engine was delivering more force than the machinery needed at that instant, The surplus did not go to waste. It went into accelerating the wheel very slightly, stored as rotational motion in that heavy rim. Then, between strokes, as the piston's push fell away and even through dead center, the wheel's own momentum carried the crank forward, releasing that stored motion back into the system. The engine's own uneven breathing, in effect, got absorbed and smoothed out by a mass that was reluctant to change its speed quickly in either direction. What came out the other side, at the pulley, was not the jerky push of a piston, but something close to a steady, continuous rotation. A flywheel's usefulness is determined by where its weight sits, not by how much of it there is. A pound of iron sitting a few inches from the center of the wheel contributes almost nothing to its ability to store and release rotational energy because it is barely moving relative to the axis. That same pound of iron out at the rim, sweeping through a wide circle with every revolution, is doing the real work. Engineers understood this early, which is why flywheel design trended, almost from the start, toward wide-diameter wheels with comparatively thin spokes and a heavy, thick rim, rather than toward solid iron discs of the same total weight. A lighter wheel with its mass concentrated at the edge could outperform a heavier, evenly distributed one simply because of where the iron was placed. There was also a second, related lesson buried in the design of these wheels, one that took longer for the industry to fully absorb. A flywheel does not just smooth out a jerky engine, it also acts as a reservoir, a bank of stored motion an engine can draw on for a moment when a machine downstream suddenly demands more force than the piston alone is delivering at that instant. A loom snagging, a press meeting a thicker piece of stock, a saw biting into a hard knot in the wood. Without that reservoir, a sudden spike in load could stall the whole engine. With it, the wheel gave up a slice of its stored motion, carried the system through the demand, and kept turning. The bigger and heavier the wheel, within reason, the deeper that reservoir, and the more forgiving the whole mechanical system became. And once that principle was understood, the obvious next question for any mill owner or engine builder was how much smoother, how much more powerful, how much more capable a system could become if the wheel got bigger. A larger flywheel could smooth out a bigger engine. A bigger engine could drive more shafting. More shafting could turn more machines. Through most of the 19th century, the answer to almost every ambition in mechanized industry ran straight back through the size of the flywheel at the center of the plant. And it is that same upward trend, mill after mill, decade after decade, that eventually produced wheels large enough and fast enough at the rim to do exactly the kind of damage this history remembers. That upward climb reached one of its most public and most celebrated moments in 1876 in Philadelphia at the Centennial Exposition marking 100 years of the United States. Inside Machinery Hall stood an engine built by George Corliss that was, by any measure available at the time, extraordinary. It stood over 45 feet tall. Its cylinder bore was 44 inches across, with a piston stroke of 10 feet, dimensions that dwarfed anything most visitors had ever stood next to. Running at a modest-sounding 36 revolutions per minute, it produced roughly 1,400 horsepower. And at its heart sat a flywheel weighing 56 tons, 30 feet in diameter, with a rim 2 feet wide, spinning steadily at the center of the hall like the mechanical equivalent of a heartbeat for the entire exposition. Visitors who walked into Machinery Hall were not looking at a single exhibit among many. They were looking at the source of motion for the entire building, a single wheel, and the engine turning it accounting for every belt, every shaft, every working machine on display, across acres of floor space. Nothing else in the hall moved unless that wheel was moving first. That single engine, through more than a mile of connected shafting, powered 13 acres of machinery inside Machinery Hall, running lathes, looms, printing presses, pumps, and countless smaller exhibits simultaneously, all of it drawing its motion from one central source. At the exposition's opening ceremony, President Ulysses S. Grant and Emperor Dom Pedro II of Brazil together started the great engine, and for 6 months it ran continuously, driving the largest concentrated demonstration of American industrial capability the public had ever witnessed in one room. When the exposition closed, the engine was not scrapped or forgotten. It was shipped back to the Corliss Works in Providence, Rhode Island, and 7 years later it was sold to the Pullman Company in Chicago, where it went on running that factory until 1910, more than 3 decades of continuous service from a single central power source and its one great flywheel. The Corliss engine also represented a real technical advance in how steam itself was metered into the cylinder. Earlier engine designs admitted and cut off steam relatively crudely, which meant power delivery, even before you account for the piston's dead center problem, could be irregular from stroke to stroke. The Corliss valve system allowed far more precise control over exactly when steam entered the cylinder and when it was cut off, which meant the power arriving at the crank in the first place was steadier and more predictable. Pair that improved valve control with a large, well-built flywheel, and you had, for its era, about as smooth and dependable a source of rotational power as industrial technology could offer. It is no accident that Corliss engines and large flywheels became a standard pairing across American industry in the decades that followed, including at the very mill complex in Manchester, where this story will return. This central power model, one engine, one flywheel, one network of line shafts, pulleys, and belts reaching through multiple floors and sometimes multiple buildings, became the standard architecture of industrial power for most of the 19th century and well into the 20th. Nowhere is the scale of that dependence clearer than at the Queen Street Mill in Burnley, England, where a single 500-horsepower coal-fired stationary steam engine, through its shafting, drove 600 separate Lancashire power looms at once. One engine, one flywheel, absorbing and releasing the pulses of that engine's power strokes. 600 machines, each entirely dependent on the health of that one central system. It was, in the plainest sense, one heart supplying motion to hundreds of limbs, and everything admirable about this system, and everything dangerous about it, comes from the very same design choice. Put all the power, and eventually a staggering amount of stored energy, into one central spinning mass. The instinct that made these wheels so effective, bigger diameter, heavier rims, higher rotational speed, was also, without most 19th century engineers fully appreciating how sharply the numbers moved, the same instinct that made them progressively more dangerous. The energy a flywheel holds does not track its weight or its speed in a straight line. It depends on how that weight is distributed relative to the center, which is why rim mass mattered so much more than mass near the hub, and it depends on the square of the wheel's rotational speed, which is a detail that changes everything about how these machines behaved. Take that second part first, because it is the one that quietly governed nearly every flywheel disaster in this era. Double a flywheel's rotational speed, and you do not simply double the energy locked up inside it. You quadruple it. A wheel spinning only a little faster than its designers intended is not carrying a little more stored energy than expected, it can be carrying dramatically more, energy that has to go somewhere the instant the iron holding it together gives way. This is precisely why governors, the mechanical devices meant to hold an engine's speed steady under changing load, mattered so enormously to safety and not just to product quality. A governor that failed, or a load condition that let an engine run away even briefly, did not create a proportionally small safety problem. It created a compounding one. A 10% overspeed sounds, to an untrained ear, like a minor mechanical hiccup, the kind of thing a mill engineer might note and correct without much concern. Run the numbers on stored energy, and that same 10% translates into an increase of roughly 21% in the energy the wheel is carrying. Energy the rim, the spokes, and the hub all have to physically restrain through nothing more than the tensile strength of the cast iron itself. Push the overspeed higher, and the energy climbs faster still, curving upward far more steeply than the speed number itself suggests. A wheel does not have to run away wildly to become dramatically more dangerous. It only has to run away a little, for long enough, while nobody manages to bring it back under control in time. The other half of the equation, where the mass sits, explains why engineers pushed flywheel design toward wide, heavy-rimmed wheels in the first place. Iron sitting close to the axle, spinning in a tight little circle, contributes almost nothing to the wheel's stored energy, no matter how much of it you pile on there. Iron out at the rim of a 30-foot wheel is moving through an enormous circle with every single revolution, and that motion is where nearly all of the wheel's usable, storable energy lives. This is also, inconveniently, why the outer edge of a large flywheel can be moving at a startling speed even while the wheel itself looks, to anyone watching it turn, slow and stately. A 30-foot diameter wheel does not need a high number on a tachometer to have a rim slicing through the air at well over 100 miles an hour. The eye sees a heavy iron wheel turning at a calm, almost hypnotic pace. The physics sees tons of iron moving as fast as a car on a highway, restrained only by the tensile strength of the metal holding the rim together against the force constantly trying to fling it outward. That restraining strength is where the material itself becomes the weak link in the whole system, because the overwhelming majority of 19th century flywheels, including the largest and most celebrated ones, were cast iron. Cast iron earned that dominance for practical reasons. It was inexpensive relative to alternatives. It could be poured into large, complex shapes that would have been enormously difficult to forge or machine any other way, and it performed well under compression, which made it a natural fit for heavy structural castings. But cast iron carries a serious limitation that has nothing to do with how carefully it is used and everything to do with what it is. It is brittle. It tolerates very little tension before it fails, and it has almost no tolerance at all for internal flaws, the kind of hidden porosity, trapped gas pockets, and cooling stress cracks that can form invisibly inside a large casting as the molten iron cools unevenly from the outside in. Foundry workers pouring a casting this large were, in effect, fighting the physics of cooling metal itself. Molten iron poured into a mold this size does not cool evenly. The outer surface against the mold hardens first, while the interior remains molten longer, and as that interior finally cools and contracts, it can pull away from the already solid metal around it, leaving behind exactly the kind of internal gap or crack that no amount of skill at the pour could reliably prevent. This was a property of casting iron in large masses at all, not a matter of careless foundry work, one that the industry understood in general terms without ever developing a dependable way to inspect for it after the fact. A flywheel rim cast with one of these hidden flaws could look completely sound. It could pass every visual inspection anyone in the 1800s knew how to perform. It could run for months or years without incident. And it could still be carrying, buried in its own iron, a weak point sitting exactly where stress concentrated most once the wheel reached high rim speed. A flaw nobody on the factory floor had any reliable way to detect, because there was no practical means at the time to see inside a solid iron rim and confirm it was sound all the way through. Engineers of the period set their safety margins based on the known tensile strength of good cast iron, and they generally believed those margins were conservative. Reality kept proving them wrong, because the margin only holds if the iron in front of you matches the iron in the textbook. And a hidden casting flaw meant it sometimes did not, and the wheel could fail at speeds well below what its designers had calculated as safe. Put all three pieces together, and you can see exactly how a machine engineered specifically to smooth out danger and irregularity in a factory became, at sufficient scale, a source of danger all its own. More rim mass meant more stored energy and smoother running, and also more energy waiting to be released if something gave way. Higher rim speed meant smoother, more powerful central drive, and also, because energy scales with the square of that speed, a rapidly compounding amount of stored force behind even a modest overspeed. And cast iron made all of it affordable and buildable at the scale 19th century industry demanded, while quietly guaranteeing that some fraction of these wheels, built exactly according to the standards of the day, were spinning at high speed with a flaw already sitting inside them that no one could see and no one could fully guard against. A flywheel running normally at its intended speed in sound iron was one of the safest and most valuable pieces of machinery in any mill. The same wheel, running even modestly too fast or cast with a defect no inspection could catch, was something else entirely, and the people working closest to it had almost no way to know, from the outside, which kind of wheel they were standing next to on any given morning. They were standing very close to it as a matter of routine. The mills built around this central power architecture were loud, crowded, and full of rotating machinery that ran largely unguarded by the standards of any later era. Overhead line shafts turned continuously at head height and above, spinning pulleys studded the walls and ceilings throughout the building, and leather belts, some of them running at considerable speed, crossed walkways and work floors as a normal feature of the environment rather than an exception to it. Workers, sometimes very young workers, spent their entire shifts in close physical proximity to exposed rotating shafts, pulleys, and belts because there was, structurally, no way to build this kind of factory without them. Every machine on the floor depended on a mechanical connection reaching back eventually to the one central engine and its flywheel, and that connection had to travel through the same space the workers occupied. Injuries from becoming caught in unguarded shafting, pulleys, and belts, a hand or a sleeve or loose hair drawn into moving machinery, were a well-documented and recurring hazard of this entire industrial system across American and British mills in this era, not an isolated failure at any one plant. It was a known cost of working inside a building where power moved everywhere at once, through exposed iron and leather. Workers learned the geography of danger in their own mill the way people learn a familiar street, which shaft ran close overhead on which walkway, which belt whipped past at ankle height near a particular machine, which pulley was better given a wide berth than a close one because the building itself never stopped moving around them for the length of a working day. And because the whole system was interconnected, running from one central source out to every machine on the floor, maintenance often could not wait for a convenient, fully powered down moment. Stopping the main engine meant stopping every single machine fed by its shafting. An entire mill's production halted at once, not one idle machine but the whole building idle simultaneously. That made a full shutdown for inspection or repair an expensive decision one owners were reluctant to make more often than strictly necessary, which meant repairs and adjustments were frequently carried out with the system still running or only partially stopped, workers moving among live shafts and belts to do the job rather than waiting for silence that came at a real production cost every time it was called for. And even when a genuine emergency did call for the system to stop immediately, it could not in an instant. A flywheel carrying tens of tons of iron at speed does not surrender its momentum the moment steam is cut off. It takes real time, real distance of continued rotation to spin down, because the same stored energy that made it useful for smoothing power delivery made it equally resistant to stopping on demand. Shutting off the engine slowed the system down. It did not freeze it. In the earliest moments of any sudden failure, whatever was already in motion stayed in motion. Belts still running, shafts still turning, the great wheel still carrying its own momentum forward, whether or not anyone wanted it to. All of that, the crowded proximity of workers to exposed drive machinery, the economic pressure against stopping the system, and the simple physical fact that a machine this massive cannot be made to stop instantly, converged inside Mill Number 7 at Amoskeag on the morning of October 15, 1891. The Amoskeag Manufacturing Company was, by that point, one of the largest textile operations in the country, a sprawling complex of connected mill buildings strung along the Merrimack River in Manchester, New Hampshire, employing thousands of workers across its various departments, all of it strung together and powered from a shared central plant. A pair of large coreless engines, each with 36-inch cylinders, generated roughly 2,000 horsepower combined, all of it gathered and smoothed by a flywheel reported at somewhere between 64 and 68 tons. Sources from the period differ slightly on the exact figure, and distributed outward through multiple belts, including that main belt 42 inches wide, to mills number 4, 5, 7, and 8. It was, in essence, a Queen Street mill on a larger and more consequential scale, one engine system, one enormous flywheel, an entire industrial complex leaning on its steady rotation. This was not an untested system running for the first time. 3 years before, in 1888, the same engine system had already failed once with fatal consequences, killing an engineer named William Venable. The details of that earlier incident are thin in the historical record, but the fact of it is not. This was a machine that had already taken a life before that morning in October 1891, and it had gone back into daily service afterward, because stopping it permanently meant stopping the mill. On the morning of October 15, something in the power delivery through the complex began to go wrong. Belts started overheating, without an obvious cause visible to the people on the floor. Sparks began flying from the wide main belt. The great flywheel was climbing in speed, turning faster than it was meant to run, and the effects of that instability were not uniform across the mill, which made the problem harder to read in the moment rather than easier. In the southern end of the complex, carding machines were slowing down. In the northern end, at the very same time, looms were speeding up, dangerously so, and at least one loom's own governing mechanism, the local safeguard meant to keep its speed under control, failed to hold it in check. 10 years is long enough to know a machine's ordinary moods, the sounds and vibrations that mean nothing, and the ones that mean something, is beginning to go wrong. Samuel J. Bunker, the mill's engineer, a man with that decade of experience in the position and well regarded by those who worked with him, went down into the power pit to investigate the trouble directly, at the source, among the shafting and the engines themselves, doing exactly what an engineer with his experience was supposed to do when the machinery under his care started behaving in a way he could not explain from the floor above. An assistant engineer, recognizing the danger in the flywheel's climbing speed, attempted to cut power to the system. It was, by every account, the correct response to a wheel that was overspeeding. It was also, given how much momentum tens of tons of iron carry even after steam is shut off, a response that could not arrest what was already happening fast enough. Moments later, the flywheel let go. It tore itself apart under the load its own excessive speed had put on it, and the stored rotational energy inside that iron, energy that had been quietly accumulating with every increment of overspeed, tore loose all at once, in less time than it takes to complete a single word. Fragments of the wheel, pieces of iron weighing enormous amounts individually, ripped free at whatever speed the rim had reached in its final moments and were hurled roughly 200 feet from the point of failure, crossing that distance in a fraction of a second. The second floor of mill number 7 caved in under the force. Metal fragments punched through the roofs and windows of neighboring buildings. Timbers came down with the floor. Steam screamed out of ruptured lines running through the pit and the floors above it. None of it was the work of an explosion in the ordinary sense, no combustion, no chemical blast. It was decades of accumulated rotational energy, the same kind of energy that had spent years quietly smoothing the mill's power delivery, finding an exit all at once through a crack in the metal that had been waiting, unseen, since the day the wheel was cast. 3 people were killed. Samuel J. Bunker died instantly, down in the power pit where he had gone to investigate the very trouble that then killed him. Ada, also recorded in some accounts as Ida Cram, died later at Elliott Hospital of a head injury sustained in the collapse. Mary Kane, 21 years old, died of a fatal injury to her scalp and head. At least 8 other workers suffered broken bones and serious injuries in the same event, and among the injured was a boy of 12, a reminder that the mill's workforce, like so many of its era, included children working alongside adults inside a building where an iron wheel weighing tens of tons had just come apart. A coroner's jury investigated the disaster afterward, and engineers examined what remained of the wreckage. What they found inside the broken iron were irregularities left over from the original casting process, gaps and flaws baked into the metal from the moment it was poured. Decades of quiet weakness, sitting inside a wheel that had, by every visible external measure, looked sound. The investigators could not reach a fully conclusive account of exactly how the failure sequence began. Their best assessment, offered as the most probable explanation rather than a proven certainty, was that a gradual failure somewhere in the belt connecting mechanism had likely produced the erratic, cyclical power fluctuations reported that morning, the uneven slowing in the south end and speeding in the north, and that those fluctuations had progressively overloaded the flywheel until it exceeded a safe rotational speed and, meeting the hidden weakness already inside its own casting, burst. No blame was assigned to Bunker, and none was assigned to the company by the coroner's jury that reviewed the evidence. Amoskeag was not an isolated case, even if it remains one of the most fully documented. Flywheel bursts of this kind were a recognized, recurring hazard across American and British industry through this period. The same underlying pattern of high rim speed, brittle cast iron, and undetectable internal flaws playing out at other plants as well, including a documented flywheel accident at the Providence Rubber Shoe Company in Providence, Rhode Island. The specifics differed from incident to incident, but the shape of the danger did not. A central wheel, essential to production, trusted for years, failing suddenly and without meaningful warning once its speed or its metal crossed a threshold nobody could see coming from the outside. And still, mills kept running these systems, for reasons that had nothing to do with indifference and everything to do with what the alternative cost. For most of the 19th century, central steam power, one large engine, one great flywheel, a mill-wide network of shafting reaching every machine, was the best industrial technology available. Nothing else could deliver that volume of continuous mechanical power to hundreds of machines at once. Taking a central flywheel fully out of service for the kind of thorough interior inspection that might have caught a casting flaw meant stopping every machine in the mill that depended on it. A production halt across the entire complex rather than a single idle station, and mills absorbed that cost only when they had to, not as routine preventive practice. That inspection would have cost a mill the size of Amoskeag dearly. Pulling the flywheel out of service was not a matter of shutting down one loom while the others kept working. It meant every carding machine, every loom, every piece of equipment fed by that shaft network across those 4 mill buildings went silent at once, for as long as the inspection and any necessary repair took, with no product coming off any of those machines and no way to shift the work elsewhere, because there was no elsewhere. The whole complex ran off the same wheel. Weighed against that kind of complete, multi-building stoppage, the temptation to keep a known engine running, watching it, adjusting it, trusting the margins its builders had calculated, rather than pulling it apart to search for a flaw nobody could even guarantee was there, reflected the economics of the system more than any disregard for the danger. Caution and continued operation looked, from week to week, like the same reasonable choice, right up until the week it was not. Replacing or fully rebuilding a central power system entirely was slower and more expensive still, which meant an engine and flywheel already known to carry some risk, sometimes a documented risk with a name and a date attached to it, as at Amoskeag in 1888, often kept running rather than being pulled from service, because the statistical odds of failure on any given day were low, even while the consequence, when it did happen, was severe. That calculation did not go unchallenged after events like Amoskeag repeated themselves across the industry. Engineering practice shifted in the decades that followed, not through any single dramatic reform, but through a steady accumulation of more conservative standards. Steel and improved iron alloys, materials with far more tolerance for internal stress and far less brittleness than plain cast iron, gradually displaced cast iron for the most heavily loaded flywheel rims. Rim speed limits and safety margins were set more conservatively, with less confidence placed in the older assumption that theoretical tensile strength alone was a sufficient guarantee. Governors improved, giving engines tighter control over rotational speed and reducing the chances of the kind of overspeed event that had preceded the Amoskeag failure. Inspection practices improved as well, even without a perfect way to see inside solid iron. And physical containment measures, recessed power pits built to direct and absorb debris rather than let it travel freely, additional guarding around exposed machinery, became more common, an acknowledgement that even a well-built, well-maintained flywheel could not be guaranteed never to fail, only made less likely to, and its failure, if it came, at least partially contained rather than left to travel 200 feet through open mill floors. None of that engineering caution, however, was what finally ended the era of the giant central flywheel. What ended it was a better system arriving to replace it. Electric motors changed the fundamental architecture of factory power, though not overnight and not by simple substitution. In their earliest years, only large electric motors were practical to build and install, so the first electrified factories still used one large motor to drive the same kind of central line shafting the steam engines had always driven. The wiring and the power source changed, but the belts, the pulleys, and the single point of mechanical failure largely stayed the same. It was only after roughly 1900, as smaller and cheaper individual electric motors became practical, that factory design began to change in a more fundamental way. New installations increasingly abandoned the single central engine entirely, in favor of what came to be called unit drive, a small motor mounted at or near each individual machine, rather than one great engine and flywheel feeding power outward through a mill-wide web of shafts and belts. Where a single overhead shaft had once reached across an entire floor, carrying its constant risk to everyone working beneath it, unit drive replaced that shaft with nothing more than a wire, and the difference showed up immediately in how the factory floor itself could be organized and how it felt to work on it. Unit drive replaced the old central wheel not because regulators or reformers banned it, but because on nearly every practical measure that mattered to a factory owner, it was the better system. Firms that made the switch from shaft and belt power to individual electric drive documented meaningfully less worker sick time and real increases in production, using the very same machinery they had always run, machinery that now moved when its own motor turned it, not when a shaft somewhere else in the building happened to be turning. Machines could finally be arranged on the floor according to the logic of the workflow itself, rather than being chained to wherever a length of shafting happened to reach. A single machine could be started or stopped instantly, on its own, without shutting down production anywhere else in the building. And with that change, the specific failure mode that had killed 3 people at Amoskeag, one central mass of spinning iron, tens of tons of it, carrying enough stored energy to tear through walls and floors if it ever let go, disappeared from the ordinary factory floor. By the middle of the 20th century, most line shaft systems had gone out of service entirely, and very few examples survive intact today. But the principle that made the great mill flywheels valuable in the first place, a spinning mass storing surplus energy and releasing it back when it is needed, never went away. It only left the factory floor, and it moved into settings engineered far more carefully around exactly the danger that Amoskeag exposed. Flywheel energy storage exists today in grid-scale installations, holding short-term reserves of energy and helping stabilize the frequency of electrical grids that, much like a 19th-century line shaft, need their power delivery kept smooth and steady rather than jerky and uneven. It exists in uninterruptible power supply systems, including diesel rotary installations, where a spinning flywheel bridges the brief gap between a power failure and the moment backup generation comes fully online, doing, in miniature and under careful control, exactly what the wheel at the center of the Amoskeag mill was doing on a much larger and far less controlled scale, carrying a system through the gap where power would otherwise falter. The scale, of course, is nothing close to what stood in the power pit at Amoskeag or under Machinery Hall in Philadelphia. Modern flywheel storage systems are built for measured, contained bursts and steady regulation, not for driving a mile of shafting across 13 acres of machines. But the underlying bargain is identical to the one 19th-century engineers were making without fully realizing how exposed it left them. Accept the risk of holding a large amount of rotational energy in one place in exchange for the ability to release it smoothly and precisely when a system needs it most. What separates a modern installation from Amoskeag's mill is not the physics, which has not changed at all, but the engineering discipline wrapped around it, the acknowledgement, built into the design from the start, that stored energy on this scale must always be assumed capable of getting out. What has changed is the material and the containment, the two factors that turned Amoskeag's wheel from a solved engineering problem into a fatal one. Modern flywheels are commonly built from carbon fiber composites rather than brittle cast iron, materials engineered specifically to fail differently even if they do fail, and they are typically enclosed in sealed containment housings, built on the explicit assumption that a failure is always possible and must be planned for, not simply hoped against. If a modern flywheel does come apart, it is designed to break into small, contained fragments inside its housing, rather than releasing an intact multi-ton mass of iron outward at highway speed into open space the way the Amoskeag wheel did in 1891. There is no single careless villain in this account. There was an engineering standard that trusted a margin calculated from good iron, a manufacturing process that could hide a flaw inside good iron without ever showing it on the surface, and a business model that made a full teardown of an already suspect system, one that had already killed once in 1888, a cost mills kept choosing to defer rather than absorb, right up until the deferral ran out. The wheel that came apart in Manchester was never a flaw in the idea of the flywheel itself. It was the same idea, the same physics, the same storage of rotational energy that smoothed the jerk of a piston engine and let one machine drive hundreds of others, pushed to a scale and a speed that the cast iron of its day could not always be trusted to hold, and built without any way to see the crack already waiting inside its own metal. Every gain that made these wheels worth building, more mass at the rim, more diameter, more speed, was also, by the same physical law, a gain in exactly what made them dangerous when something inside them finally gave way. That contradiction sat quietly inside every mill running one of these systems, present on the calm mornings and the ordinary shifts, just as much as it was present on October 15, 1891, waiting for the specific, undetectable failure that would let it out. The wheels that still spin today, sealed inside composite housings, storing power for a hospital's backup system or a stretch of electrical grid, are the same technology that spun in Manchester in 1891, still carrying the same lesson Amoskeag paid for in iron, timber, and 3 lives, that a slow and steady turning wheel can be quietly holding far more force than it looks like it could ever need to let go.